You've probably never stopped to think about it, but that metal box that reheats your lunch, your microwave oven, is proving at this very moment that the universe has an inviolable speed limit. I'm not talking about some distant theory or philosophical speculation you read in a science fiction book. I'm referring to a pure and verifiable fact of physics that manifests itself every time you press the start button and hear that characteristic hum. The inconvenient and wonderful truth is that the functioning of this seemingly banal household appliance is intrinsically linked to one of nature's most fundamental constants, the speed of light. It's such an elegant and powerful demonstration that, after understanding it, you'll never look at your kitchen the same way again. The act of heating a plate of food will become a cosmic experiment. That melted cheese or that steaming soup is actually the result of a precise dance between energy and matter, governed by a universal law that dictates the rhythm of all existence, from the glow of a light bulb to the explosion of a distant star. The evidence for Einstein's greatest discovery isn't in a billion-dollar Swiss laboratory, but right there, next to your refrigerator, waiting to be understood in all its glory. Think about how routine the use of a microwave is. You throw the food in, press a few buttons, and in a few minutes, the magic happens. But what magic is that exactly? Most of us take it for granted, a convenient mystery of modern life. It's just technology. But that word, technology, is often a refuge from having to understand things. We trust that the food will come out hot, but we rarely ask ourselves why. How can a box without fire, without a visible incandescent heating element, heat a dish from the inside out in such a strange and sometimes uneven way? Why do some parts boil while others remain cold? This phenomenon, which many of us attribute to a defect in the appliance, is actually the most crucial clue. It's the X on the treasure map. It's the signature of a fundamental physical principle in action. This appliance isn't just heating your food, it's delivering a silent lecture on the nature of waves, energy, and the very structure of space-time. And the most fascinating thing is that you can decipher this lecture with a little curiosity and, perhaps, a slice of cheese. The mystery of uneven warming is not a bug, it's a feature of the universe. I've always believed that if you can't explain something simply, you haven't understood it well enough. My work, and my great passion, has always been to unravel the puzzles that nature presents to us, not for a select group of academics, but for anyone who has the audacity to ask why. The beauty of physics lies not in complicated equations, but in the ability to see the world through them, to perceive the universal workings behind the simplest phenomena. And that's exactly what we'll do here. We'll take this everyday device and use it as a lens to observe one of the deepest laws of reality. Don't worry, we won't drown in jargon or impenetrable mathematics. We'll use imagination, analogies, and a genuine desire to understand. I firmly believe that science belongs to everyone, and the joy of discovery is a fundamental human right. So forget for a moment that we're talking about cutting-edge physics. Imagine we're just two curious people trying to understand how a magic box works. And in the process, we will stumble upon a truth about the cosmos that will forever change our understanding of everything. The journey begins now. To begin, we need to talk about waves. Forget electricity for a second and imagine a long rope stretched between you and a friend. If you swing your hand up and down, you'll create a ripple that travels along the rope. That's a wave. It has some important characteristics. One is frequency, how fast you swing your hand up and down. If you swing quickly, the frequency is high. If you swing slowly, the frequency is low. Another characteristic is wavelength, the distance between two consecutive crests of the ripple. If you swing your hand quickly, high frequency, the waves are shorter and more compressed. If you swing slowly, low frequency, the waves are longer and more spaced out. Notice the inverse relationship: high frequency, short wavelength; low frequency, long wavelength. Now, the crucial point is that the speed at which this ripple travels along the rope depends only on the rope itself, its tension, its thickness, and not on how fast you swing your hand. The speed is constant for that specific rope. You can change the frequency and wavelength, but the wave speed remains constant. It is this fundamental relationship between frequency, wavelength, and constant speed that lies at the heart of our microwave mystery. Now let's replace the rope with something invisible, yet omnipresent: the electromagnetic field. Just as a disturbance in the rope creates a mechanical wave, a disturbance in the electromagnetic field creates an electromagnetic wave. And what is an electromagnetic wave? The light you see is one. The radio waves that bring music to your car are another. The X-rays that reveal your bones, the infrared rays that warm you, the ultraviolet rays that tan you. All of this is fundamentally the same thing. They are ripples in the electromagnetic field. The only difference between them is the frequency, and consequently, the wavelength. Radio waves have very low frequencies and long wavelengths, which can be the size of buildings. Visible light has a much higher frequency and a tiny wavelength, smaller than the thickness of a human hair. And microwaves? They fit comfortably between radio waves and infrared. They are perfect for communication, such as Wi-Fi and cell phones, and of course, for heating food. The important thing to understand is that all of them, without exception, travel in a vacuum at exactly the same speed, the speed of light. It is the constant speed of the universal electromagnetic string. The idea that light has a finite speed and that electricity, magnetism, and light are manifestations of the same thing was one of the greatest intellectual revolutions in history. For a long time, people thought the speed of light was infinite. But in the 19th century, a brilliant Scottish physicist named James Clerk Maxwell, while tinkering with a set of 4 seemingly unrelated equations describing electrical and magnetic phenomena, made a jaw-dropping discovery. By unifying these equations, he realized they predicted the existence of electromagnetic waves propagating at a very specific speed, which he could calculate from laboratory constants. The number he obtained was approximately 300,000 kilometers per second. This number perfectly matched the speed of light, which had already been experimentally measured. It was a eureka moment for all of humanity. Maxwell realized that light was an electromagnetic wave. This discovery paved the way for Einstein and his theory of relativity, which elevated the speed of light from merely a wave speed to the cosmic speed limit, the maximum speed at which any information or matter can travel through the universe. An idea that was born in equations on a piece of paper in Scotland. So, how does this apply to your kitchen? Inside your microwave is a device called a magnetron. Think of it as the equivalent of your hand swinging a rope, but in an incredibly precise and fast way. The magnetron is designed to generate electromagnetic waves with a very, very specific frequency, about 2.45 gigahertz, or 2.45 billion oscillations per second. This is a standardized frequency in the industry precisely because it is very well absorbed by water, fat, and sugar molecules, the main components of our food. So, when you turn on the appliance, the magnetron begins to flood the metal chamber with these microwaves. The metal casing acts like a mirror, reflecting the waves in all directions, ensuring that they reach the food from all angles. The turntable, in turn, exists to try to distribute this energy more evenly, moving the food through the different regions of wave intensity. The whole process is a direct and brilliant application of Maxwell's discovery. We are using electromagnetic waves of a controlled frequency to transfer energy directly to the food molecules, causing them to vibrate and consequently generate heat. It is a heating process fundamentally different from a conventional oven, which heats the air around the food. Here's the really ingenious part, where the uneven heating cue comes into play. Because the casing is metallic and reflective, the waves generated by the magnetron bounce off the walls. When these reflected waves meet the waves that are still being emitted, they interfere with each other. In some places, the crests of the waves add up, creating points of maximum energy, the hot spots. In other places, the crest of one wave meets the trough of another, and they cancel each other out, creating points of minimum energy, the cold spots. The result is a fixed pattern of standing waves inside the oven, similar to the vibrations of a guitar string, which has nodes, points that don't move, and troughs, points of maximum vibration. That's why, if you remove the turntable and heat something flat, like a loaf of bread or a layer of cheese, you'll see a clear pattern of cooked or melted areas and others untouched. These hotspots are not random. They are the physical and visible manifestation of the standing wave pattern inside your microwave's cavity. and the distance between two consecutive hotspots is exactly half the wavelength of the microwaves. The proof is right there, melted in your cheese. Let's delve a little deeper, to the molecular level. Why do microwaves heat food? The answer lies in the structure of the water molecule. The water molecule, H2O, is what we call a polar molecule. It has one end with a slightly positive electrical charge, the hydrogens, and another with a slightly negative charge, the oxygen. It's like a tiny magnet, an electric dipole. Now remember that an electromagnetic wave is an oscillation of an electric field and a magnetic field. As the microwave's electric field passes through the food, it oscillates back and forth 2.45 billion times per second. These tiny water molecules, being polar, desperately try to align themselves with this oscillating electric field. They try to rotate to follow the field, like a compass trying to follow a wildly spinning magnet. In doing so, they collide with each other, rub against each other, and this friction on a molecular scale is what generates heat. It's not heat that comes from outside, it's heat generated from within, from the agitation of the food's own molecules. It's an incredibly efficient method of energy transfer. A true molecular dance choreographed by an invisible force that you yourself unleashed by pressing a button. And now, the big reveal. How does all this prove the speed limit of the universe? We have the equation that relates the speed of a wave, v, to its frequency, f, and its wavelength, l, the Greek letter lambda. The equation is simply v, f, x, l. In the case of microwaves, which are electromagnetic waves, the speed v is the speed of light, which we call c. So the equation becomes c here fxl. Now think about what we have. We know the frequency, f, of microwaves, as it is determined by the manufacturer and is usually written on a label on the back of the appliance. Approximately 2.45 GHz, or 2,450,000 oscillations per second. And as we have seen, we can measure the wavelength LL. The distance between two hotspots in our cheese experiment is half the wavelength. So if we measure that distance in centimeters, multiply by 2 to get the full wavelength, and then convert to meters, we'll have the value of L. With F and L in hand, we can simply multiply them. The result you'll get, right there in your kitchen, with a ruler and a calculator, will be a surprisingly close number to 300,000 meters per second, the speed of light. Let's do the experiment mentally, or better yet, do it at home. Take a large flat plate that fits in your microwave. Remove the ring and the turntable. Cover the bottom of the plate with an even layer of something that melts easily, such as grated cheese, slices of American cheese, or even a string of marshmallows. Place the plate in the microwave and heat on high power for a short period, perhaps 20 or 30 seconds. The goal is not to cook, but just to melt. When you remove the plate, you will notice a distinct pattern. Some areas will be completely melted and bubbling, while others will be virtually untouched. These are our hotspots, the antinodes of the standing wave. Now, take a ruler and measure the distance between the centers of two consecutive hotspots. You will find something around 6 centimeters, 0.06 meters. Since this distance is half the wavelength, the full wavelength, L, is about 12 centimeters, or 0.12 meters. Now let's calculate CR/FXL. Using the standard frequency, we have CR 2,450,000 Hz, X 0.12 manner. The result is 294,000 meters per second. This is incredibly close to the official value for the speed of light, which is 299,792,458 ms. The small difference is due to inaccuracies in the measurement and the actual frequency of your device, but the order of magnitude is perfect. You have just measured a universal constant. The most counterintuitive and profound aspect of all this is that the speed of light isn't just about light. The c in Einstein's famous equation, EmC2, wasn't chosen by chance. It represents the speed of causality. It's the maximum speed at which any information, any cause and effect, can propagate through the fabric of space-time. Nothing with mass can reach this speed, and nothing, not even information, can surpass it. When you turn on your microwave, the effect, heating the food, doesn't happen instantaneously. It takes a minuscule amount of time for the information, carried by the electromagnetic wave, to travel from the magnetron to the food. This speed limit is embedded in the most fundamental structure of our universe. If it were possible to send a signal faster than light, you could, in theory, send a message to the past, violating causality and creating all sorts of logical paradoxes. Therefore, when you measure c with your melted cheese, you're not just measuring the speed of a wave. You are probing the most basic rules of the cosmic game, the law that ensures time flows forward and the universe makes sense. Your kitchen becomes a testament to the logical structure of reality. Of course, we need to be honest as scientists. The melted cheese experiment isn't going to win you a Nobel Prize. It's a wonderful demonstration, but not a high-precision measurement. There are several sources of error. The frequency of your magnetron might not be exactly 2.45 GHz. It can vary slightly with the temperature and age of the device. The oven cavity isn't a perfect cube, and the presence of the food itself slightly alters the wave pattern. Measuring the exact center of a patch of melted cheese with a school ruler also has its limitations. Scientists use much more sophisticated equipment, such as laser interferometers and atomic clocks, to measure the speed of light with the precision of many decimal places that we know today. In fact, since 1983, the speed of light has been so well known that its value has been fixed by definition. Today we use the speed of light to define what a meter is. But this doesn't diminish the beauty of our demonstration in any way. The fact that such a simple experiment can get so close to the real value is a testament to the universality and accessibility of physical principles. Nature does not hide its laws in vaults, it displays them everywhere. The importance of the speed of light goes far beyond heating up lunch. This universal constant is woven into almost all modern technology and our understanding of the universe. Think of the GPS in your cell phone. For it to accurately determine your location, it receives signals from multiple satellites orbiting the Earth. The receiver in your phone calculates your distance from each satellite by measuring the exact time it took for the signal, a radio wave, which travels at the speed of light, to arrive. But it doesn't stop there. According to Einstein's theory of relativity, the clocks on the satellites, which move rapidly and are in a weaker gravitational field, run at a slightly different rate than clocks here on Earth. If GPS engineers didn't correct for these relativistic effects, which depend directly on the constancy of the speed of light, the system would accumulate errors of several kilometers per day, rendering it completely useless. Similarly, in astronomy, the speed of light is our cosmic ruler. When we look at the Andromeda Galaxy, 2.5 million light-years away, we are seeing the light that left that galaxy 2.5 million years ago. The speed of light allows us to be archaeologists of time, looking into the past of the universe. This brings us to a truly cosmic perspective. The same constant c that you just measured with cheese and a ruler is the one that governs the light from the most distant stars we can observe, stars whose photons have traveled for over 13 billion years to reach our telescopes. The same physical law that heats your soup is dictating the speed at which reality unfolds on the vastest scales imaginable. There are no laws of kitchen physics and laws of cosmic physics. There are only the laws of physics, period. This universality is one of the most powerful and beautiful ideas in science. It connects your small world, your daily experience, with the vastness of the cosmos in an intimate and profound way. Your microwave is not an isolated entity. It is a participant in the same universe, governed by the same rules that form galaxies, ignite suns, and curve the very fabric of space-time around black holes. There is incredible poetry in that. The understanding that the fundamental principles of nature are not confined to exotic laboratories, but are actively operating in every corner of our lives, in every device, in every breath. The universe is constantly revealing itself to us in the most unexpected places. The constancy of the speed of light for all observers, no matter how fast they are moving, leads to philosophical implications that shake our common sense. Our intuition, based on a world of low speeds, tells us that time and space are absolute and separate. A second is a second for everyone, and a meter is a meter for everyone. But Einstein showed that this is wrong. For the speed of light to be the same for everyone, something else has to give way: time and space. Time can dilate and space can contract. They are not a passive stage where the universe happens. They are active participants. Time and space intertwine in a single four-dimensional entity called space-time. And here's the craziest part. You, me, all of us, are always moving through space-time at exactly the speed of light. If you are standing still in space, relative to something, you are traveling through the time dimension at maximum speed. If you start moving through space, some of your speed through time is diverted to your speed through space, so your time passes more slowly compared to someone who has remained stationary. This idea, which seems like science fiction, is a direct consequence of that number your microwave helps reveal. What does the future hold? Understanding and manipulating electromagnetic waves and the laws that govern them is the foundation of much of our technology, and the potential is almost limitless. Today, we use microwaves to heat food and for Wi-Fi. But what about tomorrow? Research is already underway on using high-power microwave beams to wirelessly transmit energy over long distances, perhaps to power drones in flight or even to send energy from orbiting solar panels to Earth. We could develop new types of engines, such as resonant cavity thrusters, the famous EM drive, which, while highly controversial and possibly violating known laws, forces scientists to re-examine our understanding of the interaction between electromagnetic fields and the quantum vacuum. On a more fundamental scale, deepening our knowledge of the nature of C and its relationship to space-time could open doors to technologies that today sound like fantasy. Perhaps new forms of computing or ways to probe the universe that don't rely on light. Mastering the electromagnetic spectrum was the great revolution of the 20th century, and that revolution is far from over. The experimentation with the laws of physics has only just begun. Despite all that we know, the universe still holds its deepest secrets. The speed of light is a constant, but why does it have this specific value of 299,792,458 meters per second? Why not a different value? Is it an arbitrary number, a mere cosmic accident, or is it determined by some even deeper physics that we haven't yet discovered? Furthermore, quantum theory presents us with phenomena like quantum entanglement, which Einstein called spooky action at a distance. Two entangled particles can appear to influence each other instantaneously, no matter how far apart they are, which seems to violate the speed of light limit. While this doesn't allow for sending information faster than light, causality is saved by a hair's breadth. The phenomenon suggests that our understanding of locality and space-time is still incomplete. Is C really the final limit, or are there loopholes in the laws as we know them? Was the speed of light itself different in the first moments after the Big Bang? These are the questions that keep physicists awake at night. It is the mysteries that drive the next generation of scientists. What we know is vast, but what we don't know is an endless ocean. So let's recap the incredible journey we've been on. We started with a simple, slightly irritating observation. Your microwave doesn't heat food evenly, but instead of dismissing it as a defect, we used it as a clue. We discovered that this metal box works by generating electromagnetic waves of a specific frequency, and these waves, as they bounce, create a pattern of hot and cold spots. This was our first big insight. Secondly, we realized that the distance between these hot spots allows us to measure the wavelength of these invisible waves. Armed with this measurement and the frequency provided by the manufacturer, we turned to the fundamental wave equation. Speed equals frequency times wavelength. And then, the third and most powerful insight. By performing this simple calculation, we arrived at a number that represents one of the most important constants in the universe. The speed of light, the cosmic speed limit. We not only understood how our appliance works, we transformed it into a laboratory tool to verify a fundamental law of nature. Physics has ceased to be abstract and has become tangible, measurable, real. What is the practical lesson in all of this? The lesson is, don't lose your curiosity. The world is much more interesting than it seems at first glance. The next time you're in your kitchen, look around. The refrigerator works based on the laws of thermodynamics. The pressure cooker manipulates the relationship between pressure and the boiling point of water. The blender is a lesson in centrifugal forces and fluid mechanics. Science isn't just in books or laboratories. It's everywhere, embedded in the reality that surrounds us, waiting to be noticed. Nature invites us to play, to experiment, to ask questions. Don't be afraid to look silly. Why is the sky blue? Why is metal cold to the touch? Why does bread rise? Each of these questions is a gateway to a universe of discoveries. The joy is not only in knowing the answer, but in the process of finding it, in the thrill of the hunt. So, the next time you use your microwave, smile. You are one of the few who knows the cosmic secret it holds. You know you're wielding the laws of electromagnetism to fight hunger, while simultaneously proving the theory of relativity. I want to leave you with a final thought, something that has always guided my own journey. There is nothing nobler than the pursuit of understanding. There is a profound beauty in discovering how things work, in seeing the elegant simplicity behind apparent complexity. Nature has a far greater imagination than ours. It gifts us with puzzles in every leaf, in every raindrop, in every ray of starlight. And the greatest reward is that moment, that flash of understanding, when the pieces fit together and you see the world in a new and deeper way. Don't study science to pass a test or to get a job. Study science to nourish your soul. Study to experience the joy of discovery. The universe is a vast and wonderful place, full of mysteries. And the best part? You don't need a multi-million-dollar laboratory to explore it. You only need a curious mind and the courage to ask, why? Keep that flame burning. Keep questioning. Keep exploring. Because the pleasure of discovering things is one of the most important experiences you can have. I hope this little journey through your microwave has expanded not only your mind, but also your appreciation for the world hidden beneath the surface of everyday life. Physics is everywhere, and the greatest truths of the universe often reveal themselves in the humblest places. But the microwave is just the beginning. Almost every object in your home tells a fascinating story about the laws of nature. Which one would you like to uncover next? Perhaps the pressure cooker and the secrets of thermodynamics, or your cell phone screen and the magic of quantum mechanics? Leave your suggestion in the comments below. Which everyday object do you think hides the greatest secret of physics? I look forward to reading your ideas and, who knows, turning the most curious one into our next investigation. Don't forget to think about this the next time the hum of your microwave fills the kitchen. You're not just heating food, you're confirming the cosmos.